Hi, everybody. Welcome back to the Sunday evening, at least where we are Sunday evening. Terry's in Australia, so it's Monday afternoon, and he's broadcasting for us tonight. Thank you, Terry. Um, we've got a few things we've got to tell you about. We are doing really well on our scheduling. And as a result of doing really well on our scheduling, we'll take you to the calendar first. Um, Today's September 11th. Adam is going to be here, and Adam's going to be telling us about color modifiers and narrowband imaging. Adam's obviously one of the most prolific producer of educational materials regarding all sorts of image processing. So we'll always get everything, a great show from Adam. And next week, Jock's going to be here to tell us about planning our astro imaging session. You know what, Jock, are you already ready? Just share your screen and tell us just a minute or two about what you're talking about next week.
100%, Alex. Thank you so much. So if you guys can recall from my first talk, unfortunately, we ran out of time on that one. So we are going to catch up that one again and finish that off. We have some very interesting stuff to share there. I just quickly want to share my screen with you. I hope that is coming through.
Okay. Yeah, it should be coming through.
Thank you.
So this is what we're going to be talking about next week?
Yes, 100%, Alex. So I just updated this a bit to show that in part one, if you recall, we talked about target selection and getting our gear ready, if you recall correctly. And then next week, we are going to look into the image acquisition process. We're gonna unpack the whole imaging process, how you run your session. We're going to do a few nice things around sequence optimization and also a few other surprises in there. And then we must also touch a bit on post-processing, just to discuss a bit how do you manage your data, what's the best plans of attack to reduce your data in PixInsight, and then we are going to delve into a bit what makes a great image and how in your planning process, how you can plan to take some great images. So looking forward to seeing everybody next week for this. Thank you so much, Alex.
Okay, thank you. And here we go. Okay, where am I? Back to the calendar. And so we've got several other people coming up. We've finally filled the October 2nd with Warwick. He's going to be coming, telling us about the 10 tips and cheats for getting started. Ron Bretcher will be here and kind of update us on the changes in PI over the last year or so. And then we've got a whole lot of stuff coming up. A couple of things I want you to be aware of. Between now and Christmas, we're pretty full up until November 27th, December 11th, and December 18th. We need speakers. So we need you to hit the contact button and tell us who you are and what you'd like to talk about. And then the other thing I want to tell you about, as you can see, is on December 4th, we have the TAIC workshop where we give you a data set and you go download the data set. This is what we did last time. We had Eric's California Nebula and you all imaged, you all processed his stuff, you downloaded the file, stuff like that. We haven't decided quite yet what file we're going to be using, but we know we've got a lot of good imagers out there that will donate us a data set. And so the next time we do that will be on December 4th. Just a bit of trivia. It's a bit of clickbait off the internet. I noticed that we were if you add up all the subscribers we've got, you know, down here it says someplace we've got what 13,000 subscribers or something, 13.4. So sign up and be a subscriber. You would be one. No, we're of all the YouTube channels, they rank them according to the number of subscribers. We're number 1,550,000. And while that in itself doesn't sound all that impressive, that puts us in the top 9.6% of all YouTube channels. So, you know, subscribe. It's good. because you'll get notices that we're going to be having the show and things like that. But it's also cool. Maybe we'll get moved up to like 9.5% or something like that. That'd be cool. Anyway, enough of me. Let's hear from Adam. Adam, could you go ahead and start sharing your screen, and we'll get going with Adam Block. Tell us about color modifiers.
So maybe a couple of comments here. The first comment is, this presentation won't have beautiful slides like what Jacques just showed. That was a very nice slide. This is going to be more of a demonstration type of presentation. I'm just going to be working in PixInsight on PixInsight-like things. I'm going to get to the narrowband stuff, but there are two other really brief things I'd also like to point out. I always do a kind of a potpourri of demonstrations or things to share and show. The first thing I wanted to demonstrate was something about the color mask tool. This has come up continually over the past some odd years, and it's something that I had covered on my website. I have instructional videos at adamblockstudios.com, just in case you didn't know. But I didn't make it public because it's just a little bit odd. I just think that one of the scripts has a small error, and people have been living with it. But if you didn't know it, it can like bite you, and it seems like it's something that's difficult to understand, and it doesn't need to be that way. So perhaps the developer will eventually redo it. It's just been a static script that's been released with every PixInsight all the time. But let me show you what the problem is, and then once you understand it, then you can just work with it in the way that it's intended to be used. This is a color wheel, and the colors have hues, and those hues have values. So whenever you describe a particular color here in the wheel, it has numbers you can attribute to these values. So right now, when I use my little readout preview, I get values in red, green, and blue color space, if you will, color values. But I can change those values, and I can't see my thing. Oh, let me hide this. Okay. I can change what's read out here by going to my little probe and saying, oh, please give me the values in a different color space, like HSV, for example. And when I do that, you'll see that I get numbers that actually correspond to this color wheel, where if you look at the H value here, it says 0, and that is the 0 position. And then as I go around the circle, I'll have the appropriate number there that corresponds to whatever the number is over here on the circle, right? So these are the H values. But the funny thing is that the script that I want to show you here, the color mask script, if you do the thing that a lot of people will do, there are buttons, and those buttons they're just so tempting to press because they automatically do things. If you press the button here for red, it'll select the colors that are that hue. Those are the values that go from approximately, what does it say, 300 all the way over here to 60. I think you would agree that goes from magenta all the way to orange. That certainly encompasses everything that's possibly red or some version of red. So the expectation is you're going to get a wedge when you press this button to use as a color, as a mask for identifying particular colors. But when you do that, you get a different wedge. You get this wedge over here, not the wedge up above like you would expect, like was seemingly intended by those cool little buttons. So what's going on is, if you actually look at the code of the script, and I guess I scrolled down, sorry. Now I don't know where the code is. But if you look at the code of the script, you will see that the pixel math equations that it uses are in the CIEH color space. That is not the same as HSV. This little h here has different values. And that's actually what's being used in the script. So when you press the cool little buttons there for the color mask script, it's not giving you the H values, it's giving you the small h values. It's giving you, it's not giving you the big H values, it's actually putting into that little formula small h values. And so if you really want to know how I got that little arc over there, I can just change my probe over here. My little readout probe. This just proves that it really is the small h and not the big H. See, if I do CIELCH, now I'm going to report small h's. So remember, it was going from what, 300 to 60? Well, where's 300 to 60 here? 60 is right there. And then 300, you see, maybe I should zoom in for you guys. Hold on, I'm now having fun with my tool. So here's here's 60, right? Approximately. And then if I go around, you can see 300 is all the way down here. That's how I got that wedge. That's where it's getting the numbers from. It should be H values for that range, the small h values, not the big H values, as is being actually put into the formula. I think that's a mistake, but that's why you get this weird answer. I just released today a video that actually explains in some detail about the differences between the big H and little h color space, and I demonstrate some other weird things about it. That's something to know, and I guess if you're really clever, you can go in and change the code and fix the script effectively so it kind of behaves as you might expect it to. So that was thing number one. I just wanted to point out that there's a little bit of this weirdness about the color mask script that everyone just accepted through all time. But I tried in one of my videos to explain what was going on. Why does it behave that way? And I honestly think it wasn't the original intent, but I don't think anyone's approached the developer. I think I sent him an email once, but I can't be sure, to say that there was an issue.
Adam, can I interrupt you?
Yes.
With the numbers that you've got up on the screen right now,
yeah,
with 0 at the top,
that's big H.
Those are the big H numbers.
Right.
Is there a little h number version of that?
There isn't, and if you watch my video, you'll see why. In fact, I can show you the weird part. If you watch very closely here, I can prove it even on the screen. Watch what happens when I go from here. Remember, this was going from 60. Where's 60? There's 60 right here, right? Now watch the numbers as I go. 57, 50, 0. Now we're all the way to 300. We went from 60 here to 300 here, but now look how slowly the numbers change. They only change by like 15 values to get all the way down to here. The funny thing is that in the H color space, the colors that you see here on the screen are not equally dense. They're not equally divided. There is no wheel that easily shows this same kind of representation. There's a difference between a perceptual color space and one that kind of does what you see here in the H value, the large H value color space.
Okay, so if I'm using my color masking script, and yes, I want the red out of the North American Nebula,
right? Step one is to put your probe in the small h thing, as I did here. Put small h so you can read the value itself. And then you look here at these values. So red goes from an H of 79 to an H of 59. And
or if that were a picture of the North American Nebula that I was actually trying, I would use the North American Nebula.
Yes.
Okay, yeah. And I would just say, you know what, I want this particular color in the North American Nebula to be my
mask color. And the trick is to input H values. That's the trick.
Yeah. Okay.
Yep.
Thank you.
Yep. Exactly. Yeah, I don't have yeah, it can be any picture. The colors are colors. Yeah, exactly. All right. So the next thing I want to show is another kind of interesting thing. It might interest some people because this is it's a thing that always happens, right? Which is that people have strange images and they wonder why they're strange and they try to figure it out. Well, I'm often inundated with questions about this. So it's not a side of the processing that I generally show, although I can use it as inspiration to show how to fix things. But of course, all kinds of people have different equipment. And when it comes to acquisition issues, it's infinite in the number of permutations and number of different things that can happen. But one of the main points that I want to demonstrate here is that when you look at an example like this, the gentleman submitted this image to me, and the complaint was, look at him, I'm using the new version of WBPP or WBPP in general, and my flat field images, my flats are not getting rid of the donuts. As you can see here, they're not. It's true. But it sure is bizarre looking. I mean, this almost looks like, you know, the optical system has changed. It almost looks embossed, especially if you look at, you know, the donut like this, but it's not quite. It's awfully weird. And so I actually took this gentleman's data, I processed it through WBPP. Of course, I got exactly the result that he got. So the data is actually quite good. But to figure out what was going on is to apply, you know, like the methodology that I show in my videos on my site. I try to break things down and look at the simplest explanations that things can be. And so I spent time trying to do this, and I'd like to show you how I figured out basically the answer. This is, I went through all the data. This is actually the raw data. This is not calibrated at all, so that you can see here the donut, right? This is what uncalibrated data looks like. You can see that there's there's still hot pixels and satellite trails and all that kind of stuff. But can everyone, I think you can see the donut here. Here's what I'd like to show. If you step through the images here, the donut changes. Sometimes it's a half donut. Sometimes it's a full donut. What the heck does that mean? And this was the key insight for me. So I had this conversation with the person who had the data, and I tried to convince him the only way in my mind that I knew of that this could be is if something was in front of the telescope. Something big was in front of the telescope. Something was shadowing the mirror. That's the only way you can do this, is what I had in my mind. But he told me he had his nice telescope, and I can show you a picture of it, and it's in a roll-off enclosure. And he said, Adam, when I roll back the roof, there's nothing there. And furthermore, he was looking at M81, which is relatively high in the sky. You know, he was 60 degrees up in the sky. So we have this conversation about what it can be, and I'm just so convinced that something is blocking the mirror, but everything he's telling me is nothing is blocking the mirror. The last thing that we had this conversation on the phone, the last thing we did before I hang up is he said, Adam, it could be spider webs. I'm like, no, it's not spider web. So I have this conversation. I call him back a little later, and I start to probe a little more about his enclosure. So let me show you the enclosure. So this is the telescope. This is the roll-off roof. And the first question I had for him is, how far away is this telescope from the wall? And he said 16 inches. I said, whoa, that's pretty close. But it still doesn't answer why, when he was high in the sky, if this is an issue, why something would be blocking the telescope. He's got a roll-off roof. And then I asked him, well, what is the orientation of your roll-off roof? And then he told me, well, it's north-south. I thought, well, any one is in the north. I wonder. So then eventually he shows me a picture of his setup, and this is the picture that I get. And this is the picture that I get here. And I'm like, oh, okay, that's it. That's the answer. So the answer is, it was an obstruction. He is looking at the top part of the enclosure, the roof part. And the reason why it got worse when he was highest in the sky is because he was crossing the apex here of his enclosure, because his telescope is relatively close to the building itself. Now, the thing is, when you look at this image, and I flip through the images, it's just not obvious that that's what's going on. Because if you look at the stars and the galaxy in the image, they don't change very much. So one of the rules, one of the things that people should know about telescopes is that if you obstruct a telescope, the image, the formed images, things that are in focus, will not have a big effect. There is going to be effect, but it's subtle. The major effect is that you will just lessen the amount of light. You attenuate the light, whatever it is you're looking at. But when you have an automatic screen stretch like this, that's not obvious that that's what's going on. If you look very closely, you will see that when he has a half donut, the galaxy is a little bit fainter. But even with half his mirror, gathering the light, that's enough in a 10-minute exposure to still make a good galaxy picture. Now, what you will see, though, notice when we have the half donut, now you've got diffraction patterns around the stars. So you get extra diffraction every time the roof is in the way, or especially when it's more in the way. And that's another hint that, again, you have an obstruction, but it's not obvious. the way to know whether you have an obstruction is, of course, you put the images out of focus. And so that was the last thing that I asked him to do was, if you want to show where you're getting interference from your enclosure, just take pictures at these boundaries and see when your stars are out of focus. There's no easy way. You can maybe do it by eye, but that's not the precise way to do it. The precise way to do it is to get your stars out of focus and then go take pictures, and you can trace exactly where the obstruction is with respect to altitude or whatever in the sky. So this is the image that he did, and then of course he can now map where his obstruction is, and he can put it into his acquisition software so that he knows to avoid those particular parts of the sky, so he doesn't run into this problem. So again, coming back here to this original image, the original idea was, well, there's something wrong with WBPP. There's something wrong with the processing. It has nothing to do with that at all. This is a consequence of obstructed light. The flat field images were perfect, but the donuts in the data weren't. They were changing. And so when you integrate, calibrate, and integrate all of that, this is the result that you get. So I just wanted to point out a way of approaching problems, thinking about them kind of critically, and coming up with a solution. For me, it's a challenge because I'm sitting here with, I don't see the people's telescopes or their equipment. I have in my mind's eye what's going on, but I'm just sitting here in my room with my brain, and that's it. And my experience of working with telescopes and cameras to try to solve problems exactly like this. So it's a real challenge, and it's why I don't ever want to get into that business of doing it. But that's how you go about trying to figure stuff like this out. So if anyone has this problem, hopefully if they watch the video, they'll see what to do. And now on to the main thing. That was a little aside. Before I continue with that, does anyone out there, have they ever experienced that before? The key is if you have an obstruction, out of focus things will show the obstruction. That's the key.
We did have a question on your previous topic, your color filter wheel. Do you have an easy link to that, or I suggested we just Google color filter?
Yeah, you will get more.
Okay.
You'll get more color filter wheels than you know what to do with. Yes.
Okay.
That's exactly right.
Thanks.
Yeah. I think if you put color filter wheel and then specifically hue or something like that, you'll actually get the degrees on the circle. Okay. So what I wanted to show this evening, and I really appreciate this opportunity, is something that is new to me in the sense that narrowband imaging is something that I've only gotten into as far as processing more recently. I still apply the same kind of methodology that I would just in general. It's still the same kind of data. But of course, there's some different kinds of decisions that you make when you map colors of these images together to make an interesting or compelling image. And so with this, newness of the subject for me, there have been some interesting ways in which I've approached putting together images. And one of them is to manage how the colors blend together. So I'm going to point out some of the inspiration that I read later. I've been doing some things like what I'm going to demonstrate in broadband, in the broadband sense, but it becomes, I think, even more important to do these kinds of operations when working with narrowband imagery. So this data comes from Russ Croman, and it is just absolutely superb data. I made a tutorial on this on my site, so people get to actually grab this data and then go along with me. I'm basically going to demonstrate the highlights right now. So let me show you what some of the data looks like. We've got H-alpha data here. This is oxygen 3. And of course, here we have the S2, sulfur, that is of the Rosette Nebula. It's just super, super good data. And then on top of that, we also have the RGB data that would allow for the integration or substitution of stars, of just normal colored stars into there. So here's what the data looks like here. Very, very starry, of course. And that's something that needs to be kind of taken into account a little bit later on when you're ready to blend in those stars. So that's what the data looks like. And again, this is like one of these data sets where things you can almost not do anything wrong because the data is just so spectacular. And I'll be showing that to you a little bit here. One of the things to recognize that makes life easier in this sense is that because I'm not going to be using the stars from the narrowband data, I just remove them entirely from the beginning. Now, I'm not going to show that process. One of the kind of neat things about working with this data is I also got to use all of his various software that he's been producing lately, including the star removal, the star exterminator, the noise exterminator, and actually I use a little bit of his HDRMT color corrected little formula there. So it seems like it's kind of synergistic that here I get to use all of his software on his very data. So I did create starless images with his star exterminator, and this is what they look like. These are the linear versions of these starless images, and this is the starting point for blending the images together. And then, of course, I'm going to go forward from here to do the job of getting the stars in there and everything else. So the first step that I'm going to do when I have these three images, there's different ways of doing it. You can either make stretched versions of these images to blend together. That's certainly one way. The other way is to linear fit the images, because basically what I want to do is make the signal strengths in each of these channels at least somewhere in the vicinity of one another. They don't need to be exact. So one of the things I'm going to state right up front is that this demonstration is nothing about true signal strengths. I'm not in any way keeping any of that information. That's not the point of what I'm going to be demonstrating. What I'd like to show is a way to represent as much of this mapped information as you can at the expense of signal strength, at the expense of the true fidelity of how much information is there in each channel. So in other words, one channel certainly dominates over the other, but I might bring up the channel that's the weaker channel because it's nice to be able to see where that stuff is. That's kind of the idea behind modifying colors to enhance the image in some compelling way. So to do this then, certainly the H alpha, if you literally look at the values, they are the brightest. So the first step is to do a linear fit on these images. I'm going to go ahead and do that. That much I can do, and it won't take too much time here. So I just do linear fit. Where is linear fit? And we drag this to here, like that. And then I just do it to the images. Now just so you can see what it looks like to have it be done, I'm going to do one of them here. I'm doing the Sulphur. It takes a minute for it to figure it out. These images are absolutely huge. Another thing about Russ's data, if you look down here at the bottom, this says 9,000 by 6,000 pixels. I mean, it is just absolutely huge data. So if I look at the history here, you will see that I've done linear fit now on this thing twice. So the point is that these images, these starless images, have been linear fit to one another. And what that means is if I roll my cursor over a lot of these values between, say, the H alpha and here the O3, they're going to be very similar to one another. They won't be exactly the same, but they're going to be similar. And that's just going to make life easier in a moment when I put them into the color channels in Pixel Math. So that's the first thing I want to do. The next thing I want to do is actually put them in the channels here so you can kind of see what the colors look like. So what we want to, let me see, let me make sure. Yep, that's what I want to do. So I'm going to go ahead and show you just something of an example of what things kind of look like. So you can see the image is called H starless for the HA, O starless for the oxygen 3, and so on. I'm going to start typing in here, and I'll even try my little magnifier if that helps. So H starless stands for the hydrogen alpha, and if I were to do just, forget about the sulfur, if I just did hydrogen alpha, and then we did the oxygen, the O3 images for like HOO type imagery, we would just put one of these into the red, and then I need to turn off the single expression here so I can operate on the other channels, and then I can put the O3 rather into this channel, Typically, though, what people do is they will multiply it ×2 instead of just leave it as itself. So I'm going to put 2 times this here, and this just will make it a bright teal kind of color. But I need to put starless, sorry. Also won't work. Like that, that's it. That's all I need to do here to begin with. And I just want to demonstrate the kind of color that we get when we do it. So for a destination, we want to create a new image, and we also want the color space to be an RGB color as a result. I think that's it. That should actually do something if I press go. Now I will zoom out because I can't see what I'm doing. There we go. So this is going to make an image, but the image is going to be a little bit odd because the difference when I did the linear fit, the backgrounds are going to be, they're supposedly matched, but they will really not be equal to one another exactly. And so you'll get a bias in one color or the other color. So what I generally do is I would run DBE just as a kind of call it a poor man's background neutralization. It's certainly going to get rid of the bias between the channels and also any gradients with respect to them. So I'm just going to use DBE here to do that job. Now I already have a little icon here where I've placed samples around the image, and they're not in any way specially placed. All I've done is I've tried to avoid the major bits of nebulosity and then put some in spaces where it's kind of a little bit of a void or something like that. So I'll use DBE in this way, just so you can see the parameters, though, that I'm employing here. You can see I've got a big tolerance of 5. I have a little bit of a smoothing factor here, and then my samples are, reasonably large, considering this image. Then I do a subtraction, and I'm actually going to affect the image itself as a result. So that is what's going on. I'll go ahead and do it. Oh, that's just the, sorry. That's the model. And this is the result that you get. So this is like a typical HOO kind of result where we're getting just red, because that's all we put into the channel for red is the hydrogen alpha. But notice just how incredibly bright, because we've made these signals fairly similar to one another. The O3 is, especially when I'm multiplying it by 2 on top of everything else. But that is the nice kind of color that we want to try to get at the end of the day. Let's get out our screen transfer function and just show that we do have that nice teal color in there if we don't display it super, super bright. So the point now becomes, well, what can we do from here? What if we want to incorporate the sulfur? The sulfur is going to also be a red color. It's basically, another part of the spectrum very near to the H alpha. So I have taken it to be that I want to incorporate it in such a way that I want to put it in the red channel, but I also want to differentiate between the sulfur and the hydrogen. So all of this is very standard stuff, where what we're going to do here is we're going to put the sulfur into the red channel because we want it to be red. We put sulfur in here, sparkless. And then we need to decide what we're going to do with the H alpha, because how do we distinguish between them? Well, what we do is we actually put it in the green channel as well. So this would be like a version of SHO, where we're changing the value of the hydrogen in order to differentiate it from the sulfur. So we'll just add it in here, underscore starless. But the color that we actually want it to be can be whatever it is that we might want. The actual hue is whatever we might want it to be. So if we put it in both in equal strength, in the red channel and the green channel, we're going to get something that looks yellowish for those colors. But we still have the sulfur in here as well. So at the end of the day, it's not going to look entirely yellow. It'll be fairly orange looking. It's just that the the hydrogen alpha and the sulfur, they overlap one another. So together, by putting 2 in one channel and 1 in the other, effectively makes kind of like an orangish color. So that's kind of the result that we're getting. And in the same breath, I just want to mention that by putting the O3 in these 2 channels, we're again modifying effectively the blue channel, right? So the way I like to think of the green channel is it modifies the red, and it is also the modifier for the blue end. It's the thing in the middle that gives you all the intermediate colors. That's the way that I like to think about it. So I think about what can I put in the green channel that's going to modify either the red stuff or the blue stuff and give me those intermediate colors. I don't actually want a truly kind of yellow-orange color. So I can change. Well, I tell you what, let's just go ahead and do this because it's fun to do. I'm going to zoom out. We can now that we have our things in place here, I can just make another color image like this, run DBE on it very quickly, like that. Close this, yes, close this, do this. And now you can see the difference of the direction that we're heading. We were, I probably don't have them the same magnification here. There. So from HOO to SHO, I guess, we're going in this kind of direction. But then if we don't want it to be that kind of orange, yellow, orange, we don't need to include all of the H alpha in the green channel. So you can multiply it times some smaller factor and create an image that's going to give you more red in that. Did I press the button? It said failed because, why did I? Oh, because there's another point here. There. So this will give us much more red since we're not including as much H alpha in there. Let me go ahead and do my DB. I'm just going to keep doing this DBE trick because it makes it fast and easy to do. Do that. Close this. Yes. Get rid of this and show you the result. So now let's compare these two. Let's see, this one. Yep, there we go. Well, no, that's the original HLO. Let's do this. So this is the orange one. This is now by modifying the H alpha in the green channel, we brought it down. So now we're getting more of a deeper orange red for this result. Let's blink the two. Now you can see we're going in a deeper direction towards red because we've lessened it here. So all of that I think is very, very well known. And these values here, these basically these multipliers, whether we're doing a 0.3 here, or we might be doing a 2 times O here, they're kind of static. They're just, you know, whatever those values are, they're not going to change no matter where in the image you have those particular values interacting with one another, or they're being represented. The thing about an object like this, and I've approached this in a couple of other narrowband images, is that it does have this very bright, overwhelming color in either H alpha or O3. One or the other is going to be strong at any particular time. So you have kind of a weak signal and a strong signal. In this case, what I'd like to point out is that, especially if I make this a little bit darker, you'll notice that there are these filamentary structures within the nebula that are slightly red in color. And a lot of that filamentary structure is actually coming from this data right here. It's not the O3 data, excuse me, it's neither the O3 data, it's not really even the H alpha data. It doesn't have that same filamentary structure to it. It's really found in the sulfur data that we have that. And that overlays or overlies a lot of the other emission that's right in the center of the rosette. So for me, what I'm doing when I look at an image like this is I see that feature and I go, I really want that. I want to be able to see that even better and make it in some way stand out compared to the rest of the picture. And in the world of narrowband imaging, what I mean by that is to change its color, because I think of mapped color in terms of narrowband imaging, it means that I'm going to be changing the color of one thing or another in order to differentiate them. And so I would like to have intermediate colors that highlight these different structures in these different regions. That's the helpful thing for me. So one of the things, now I will point out that there is an idea of creating what I'm calling a color modifier. Other people have called it something different. So let me show you here a website. Let's go to here. So there is a web page that is called Dynamic Narrowband Combinations with Pixel Math. And he proposes something that really formalizes something that I've used in the past kind of on broadband imaging, but in a really cool way, he formalized it for narrowband imaging. And there's one key to the understanding of how to take advantage of this. So I'd like to just point this out. Look up The Coldest Nights, or the name of this thing, Dynamic Narrowband Combinations with Pixel Math. Read this. I'm going to be doing this a little bit differently. His methodology really relies on, he explains what's going on, but then he gives you pixel math expressions. I'm going to give you something a little different than a pixel math expression. Instead, we're actually going to do this in a more visual way. So that's one of the major differences here. And it's a little bit different than the way he does it more formally. But I want to say that this is the same kind of idea that I'm going to be demonstrating right now. So certainly look into that. So here's the idea. When we have two competing bright signals, in one sense, we have the H alpha and the O3 are both very bright in the center of the rosette. It might be nice to, where they overlap, to knock down on the O3 a little bit, just a little bit, because then we'll be able to see any red features that are showing up in either the sulfur or the hydrogen. We'll see more of that red structure in the very heart of the nebula. So the key takeaway here is that when we look at, now I'm going to remove these, I'm going to keep this one here, but I'm going to remove the other ones. This is where we are right now. So I'm going to lose this one and lose this one. So here's where we are right now. And the takeaway is that if you take an image like, let's do the oxygen and the O2, what I'm going to do is I'm going to just take them in their stretched form here. You can do this in the linear sense, but I'm going to take them in their stretched forms, and I'm going to actually multiply them times one another, and you'll see why that's important here. But first, I need to permanently stretch these two images. So I go down here, then I go like that. And that now becomes a permanently stretched version, which if I do that, you can see. And this is now a permanently stretched version. I'll need to undo this in a moment, but this will become a permanently stretched version when I do this. All right. And the point is that if I come back to pixel math and I just multiply these two images together, I will multiply the H starless times the O, before I screw things up, let's do this. Multiply the H, I had it, H starless times the O starless, like this. And I think if I just do same as target, this should work. Yes, it does. This gives me an image. The multiplication of the two images gives me an image where only where they both live, both hydrogen alpha is bright and the O3 is bright. That's where these values are going to show up, if you will. Because if either one of them are close to 0 or dark, it's going to make the other value, when you multiply, go to a dark value in the resulting image here. That's why we see very little of anything else except for the regions where the two colors, the two bands overlap. But keep in mind, I mean, this is occurring at the pixel level. It's not just a region. We actually have a mapping of these locations. So you'll notice that the dust lanes here are dark, because the dust lanes, they are more reddish, if you will, but they don't show up very strongly in the O3 at all. So they go very dark in this final image. That means that I can use this as a mapping. is a place to know where these two channels overlap with one another. That's the cool thing. This is going to be used as a tool that I'm going to use to modify colors. And here's how you take advantage of it. Now, I have already created this thing right here. This is the modifier. This is the multiplication of the H and the O together. I should have that thing. Now I'm going to back these up because I need these starless images. Hold on, let me back it up here. Let me shade this. Let me shade this. Okay. Oh, let's back it up though. Back it up. Yeah, this should be correct. Here's the HO. That's the one I just showed you. Let me invert it. And what I want to demonstrate, maybe if I just go back some steps here. Yeah, there it is. So that's the image I wanted to show you. That's exactly the multiplication of the two. And what I want to do with this image is I want to do the following. I'm going to come over here to, now we're going to go back to our, let's do our, this thing again. And I wonder if I can, no, I'm going to have to type it in again. So we have HS, we have this times 2 times O underscore starless, right? And then over here, we should still have that too, right? Let's make sure everyone should agree that that's what we had before. We had the H plus the S here. And then we have the H here multiplied times something less. It gave us that little bit of an orange. And then we have the O2 just doing its thing here. So the point is that where these two overlap, I want to change the color of I want to lessen the O3 so that the redder stuff shows up better. That means I'm going to take this thing that I've just created over here, and I want to put it times that. Now I call it an HO modifier, so I'm going to call it HO modifier like this. And the point is that what I want to have happen is that anytime I'm in this region, I want it to bring down the value of the O3. That means that this thing, wherever I see this stuff visually, I want it to make it a smaller value. As you know, in PixInsight, all of these values are between 0 and 1. So they're like their percentages. Well, right now, this is going to take the value and it's going to multiply it times some number, but it's actually not going to change it much. This is exactly the opposite thing that I want to have happen, because what will happen is in all these dark areas, this will actually make this thing go to 0. That's not what I want. What I want is the inverse of this, which is Control I. This is what I want to have happen. Now what happens is everywhere that we see darkness here, it's going to bring down the value in the green channel, which is going to make it less teal like we have it here. So let's demonstrate that. Let's be sure that I'm doing this, not messing things up. Do this. You've seen me do this part before. It's just my quick way to do that. And I think you'll agree that we are now seeing more, stuff in there. The contribution of green has gone way, way down, right? It's no longer even present. So I wouldn't want to use that much. That's like too much, if you will. That's too much of that effect. So we want something a little bit less than that effect. Well, what you can do is you take this image and you just change it a little bit so that these numbers, if I put my cursor here, you can see that it's actually bringing it down by values. It depends on where I put it here. But we're multiplying times 0.26, so only 26%. Well, maybe we wanted a little bit, we don't want to multiply 26%. Maybe when we want like 70% of the value or 60% of the value, right? So what you can do is you can get out, let me do curves transformation, curves, like this. And what you do is, this is the clever way of doing this, is you can just change the darkest values and give them light, however you want to think about it. Here, if you want to see you can see how I've lightened it up. Let's see, can I grab? Let me see if I can grab that again, sorry. Here they're dark, here they become lighter. So that's just going to change the amount. I can apply that to the image. And this becomes the modifier. Now, when I do the result that I was going for here, I press this button. I apologize to do this thing, but I want to show it to you so you can see the logical progression of this. It costs me like, I don't know, 10 seconds each time I do it. But now we still have teal, but we're able to see more of that, we're able to see more of the red filamentary structure in there. It's still not enough for me, though, because I want that sulfur to really stand out even more. I want to bring it out, and as you know, the sulfur at the moment, that's the filamentary stuff, and it only lives in the red channel. That's the only place it is. So what can I do? Well, I can make another kind of modifier. What I could do is make a modifier that is this one here, and this modifier is the multiplication of the H alpha and the sulfur. That's the thing that I really want to know, because I want to know, where is the sulfur really, really living? Where's all that filamentary structure? And this is the answer. This is the multiplication of those two. I didn't really do anything with the image. I pretty much just multiplied them together, and then I created a stretched version. This is let me be sure, but this should be the stretched version of the, let's see. Yeah, I must have just made a stretched version of this image. So this is the modifier. It's already been permanently stretched there, yeah. And I'll use it in this form, because unlike a moment ago where I had kind of the negative image, this time I want the positive version. This time what I want to have happen is I'm going to somehow take this image here and I'm going to multiply it times the sulfur. So this thing is called HS modifier, like that. Yeah, HS modifier. But there's another little trick, because right now what this will do is, remember, these values are going between 0 and 1. But what I want to have happen is I want the sulfur to be whatever its value is, if it's not, in other ways aligning with the H alpha, but here in the overlaps, I wanted to have that value plus whatever this maps as, plus whatever this modifier is doing. So that means I don't just multiply times this image, which is a value either equal to 1 or less, and these are all values less than 1. Instead, what I want to have happen here is this thing plus 1. That way it's always at least 1, and then more than 1 if these are in the region. Here it's only going to be 1 because it's in the black region. Here it'll be 1 plus. That means I'm now bumping up the sulfur in those regions. So I've used two different modifiers. I've used a modifier here to take care of that O3, and now I'm even bumping up the sulfur with this modifier in this form. So now we can press the cool little button like this. And I will do my trick. Here's my little DBE trick. Check. Remove this. And, oh, close this, sorry. Go like that. And there we are. So Now, this is going to be subtle. This is more subtle than where we were. Let me just show you, where we were at least and where we are now. So where we were without any modifiers is something like this. And maybe I'll use the little window thing here if I can. So if we do before and after, you can see the difference in color kind of everywhere. But the key that I'd like you to appreciate, and maybe as I go a little further, watch what happens as you increase the contrast and you change the color saturation. The hue values, the actual values that we're getting out here for the nebula, this color is different than the color that's inside the nebula because of the modification that I just made. So I'm getting different colorations depending upon where I'm bumping up or bringing down each of the channels based on those modifiers. It's a nice way to put different colors. I'm doing it modestly here. In fact, at the end of the day, if you were to take an image like where we are now and then add in the stars, you'll find that it looks somewhat like natural narrowband images. It doesn't look kind of crazy. It doesn't look like HO per se, HOO, but it doesn't look like a typical narrowband image either. It has kind of this natural thing, but something's odd about it because it doesn't, the rosette obviously doesn't teal in the center in broadband imaging. So it's a good place to start. By the way, let me just also point out that up here in the top right, there's this wonderful bubble. That is a planetary nebula that was discovered by Marcel Drechsler. So it is a known thing, but it's kind of cool that that shows up in the tails. I never knew. This is what makes Russ's data so wonderful here, that there were so many different tendrils of O3 in the tails of the rosette. I didn't know it was really that striking until looking very closely at this kind of data. So that's the point that I wanted to get to, was demonstrating how to use these modifiers to get you kind of the color space that you want to move in a direction that makes the image have these things stand out a little bit more. Let me look at my notes and see.
Adam,
Yeah.
there are a couple of questions.
Okay, yeah, it's a good place to pause because then I'm just going to show you some of the final tweaks.
To back up a little bit, question about whether you should linear fit to the brightest image.
Yeah,
because I've had that discussion before, and not everyone wants to do it to the brightest image. Sometimes the weaker image. So, what's your opinion about that?
So I think that makes sense when you're stretching the images. Remember, I'm actually still working with, you look here, these are still in linear space. I haven't stretched anything yet. So one of the interesting things about working with a linear image is I can multiply these things by anything I like 500 or 10 or whatever it is. All that matters with respect to the color is just the ratio between, the numbers that are the ratio between the color channels. So it really doesn't matter which of the things that I multiply one times the other. The only thing that matters for color's sake here is the ratio between the channels themselves, right? So working with what's kind of nice that I might be able to do other things while the images are still linear, and all I'm doing here is I'm getting the ratio that I want. By making them equal to one another, what's nice is that these numbers that I'm choosing, when I have 2 times O here, or I have 0.3 times H, in my mind, it just kind of makes sense because I had them get close to one another with respect to the brightest one. And then when I multiply something or divide by something, it just kind of, I know what that means in my head intuitively. That's all. I don't think it matters if you keep it in the linear space. Does that make sense?
I think it answers the question. And John was asking, these formulas are going to change depending on the narrowband target. Of course they will.
Yeah, but this is the thing, is that if you have a narrowband, there is no right formula. What I'm trying to show is that you make these images here, these modifiers, to do what you want. I wanted I wanted 2 things in particular. In this image, I wanted the O3 to back off a little bit in the middle, and I wanted the S2 to stand out, the filamentary structure, wherever it is, especially where it overlaps with the hydrogen alpha, I wanted it to bumped up. Now that's specific to this particular image. You might be looking at an image of, well, I don't know, the Crab Nebula or the Veil Nebula or something else. Maybe the Veil's not a good example. Those are very separated to begin with. But wherever you have colors that really overlap with one another, that's where the color bands are really on top of one another. That's where it becomes a problem. So one of the things that I worked on recently, let me just do this. Just as another example, although I don't think I did as well as I would have liked to have done it, but it's the right idea into what I'm talking about here. Is this image of 3199? This is another one of those examples where there's this overlap in the different bands of color. And if you don't in some way manage that, it's just overwhelmed entirely with one color or another color, and it's really hard to see any of the structure that's going on here, anything that differentiates it. And so I just wanted to bring up the weaker color, the weaker band, if you will, through using one of these modifiers. And I think that the Rosette Nebula, what I'm showing you now, is actually a really cool example of doing that.
You could also do this just by modifying the sections of the histogram, by making selections. I don't know if PixInsight does that. But Linda has another question, and I don't know exactly.
Let me address that, however. One of the things that by multiplying the images together, you get a mapping pixel by pixel that doesn't deal with a choice that I'm making. So the modifier, unlike a selection, that's just going to be a threshold based on brightness. But by multiplying the two images together, it really has a cool mathematical property that's different than a selection. That's all I want to say.
Okay. Linda says, why isn't Adam using rescale results, since the pixel math expression will end up being above 1? Is that true?
I don't believe any of these numbers are anywhere near being above 1.
Okay.
Yeah, no, because remember the base numbers here that I have in this image, because these are starting from these images right here. Just think about what this number is. This number right here is 0.075. So if I multiply, I never get anything close to, those kinds of numbers here.
Working on the linear images.
Yes.
I think those are the questions. So
because I just want to make clear, if you look at this expression here, when I say 1 point, let's pretend this number was 2, right? All I'm doing here is I'm multiplying 0.0 whatever times 2. That's not anywhere near 1. So there's nothing in these expressions that even approach that. And you can always tell that because if I do this image reset, these numbers are nowhere near 1, right? This is still a linear image. Nothing's clipped.
Okay.
Was there anything else?
No, I think that's it.
Okay. All right. So what I want to show you as the last things are just some of the very quick little, now that you have maybe the colors as you want them, what do you do? Well, there are a couple of things that I chose to do here. One of them is that, let me brighten this image again, is that this image is pretty bright, right? I'm actually going to show you for purposes here. Now, you know what? I'll just do it really quickly. So this image is pretty bright. What I'm going to do is, let's just say I saved this stretched image just as it is, right? So I get out my, should be here somewhere. I've forgotten which, oh, that's this one, right? Here it is. I'm going to stretch it to make it permanent. So now it's permanent. Maybe, you can make it a little darker, or you don't make it darker, or whatever it is. But one of the things that I wanted to do is to use HDRMT. You can use it maybe a little bit, once again, to put a little more contrast in the center of the nebula. And so that was one of the steps that I did. And what I basically ended up doing is the this mask, this modifier right here is actually a wonderful mask, as it so happens, for that very region where I want to bring down the brightness. So I can use this as a mask like this. And then we can use Russ's very cool script, which is the script, which is the color-corrected HDRMT. If you don't have this script, you can find it a number of places. It still exists online on the forum. Is one of the, in the tutorial section. It's one of the places you can find it. And I'm not going to do anything in particular here other than just apply it, execute it. The nice thing about the color-corrected form is it's going to keep the color saturation, but at the same time take down the overall kind of brightness there. Let's be sure that it did what I said it did. Let's see. I don't remember how bright I made my mask. That didn't do very much. I suspect that I had this brighter, like this. Can't remember, so let me just do this one more time. Script, utilities. This will really bring it down, but it's okay. I have the final result here, so I don't need to show it exactly. Color corrected, execute. Let's just do this one more time, just so you can see me bringing it down. Okay, there we go. So here's before, here's after. You can see that it really took it down, right? The brightness down quite a bit. Let's reset this. And that probably is too much, actually. So now I'm going to cheat, because now I'm going to actually show you where I was. Actually have the image here, and I'll be able to step backwards and show you the actual steps that I did. There we go. So let's look at the history here. So here's where I have an image that I guess is called a mask. That's the mask is what I called it, huh? Let me see what mask is. Can you show it to me? Where is mask? One second, let me find mask. There it is. So that's how much I made, that's how bright I made the image for HDRMT. So it wasn't that much different than what I had done here. So that was the first step. So here it is being brought down. And then I do a crazy thing with the color saturation. So let me show you what the color saturation looks like. Oh, I'm not going to run this now because it'll take time, but I do use a noise exterminator here. So these were the settings for noise exterminator. I should show you the before and after here. I don't want to run it because it does take some time, but let me just zoom in. So here is the before. Let's take a step back, I hope. Ah, there it is. So here's the before. You can see all the pixels, and here's the after. Now, probably on the stream, that's going to look overly done, but I used a little more than 50% here of the noise exterminator. Then after that, I did the crazy thing with the colors. So let me show you the colors here. So for the colors, I adjusted them with, let me show you, sorry, there. So this is what the color adjustment looks like. The color adjustment is interesting because, let me just show you here is the saturation increase in color. That's the little middle line here. And then what I do is I take what is this LAB space, so the B of the LAB color space, I can bring that down, and that's going to change the blueness of the image. So let me see if I can do this before and after. Yeah, I should be able to show you just here. So before, I believe I can do, forget how that's done here. It's there. Yeah. So before is this version where you have kind of the same version we're looking at. And here you can see the blue by bringing down this B value. It really changes the hue. It makes it a very vivid blue. This one, of course, just, that I don't want to do. The saturation just increases the color saturation across the board. And then there's this C one that I also messed around with a little bit, and it adds like this weird vividness as well. You don't want to do much with that one. But these messing around with these bands really has an interesting effect just to kind of boost the color strength there. One of the other things that I'd like to demonstrate with this image really quickly is that I employed unsharp mask because I just wanted to do it very briefly to demonstrate something that people use in, like they use it in Photoshop all the time, but you can do it in PixInsight if you'd like. So let me just show you the settings here. So here's the unsharp mask. And the way that unsharp mask works is that, you know, it's going to sharpen at a particular scale. So if you just make the standard deviation huge, this is the trick that's often done in Photoshop, where you use unsharp mask and you just put the selector all the way to the right and make the largest value. It increases the contrast of the very largest features. But the trick is, don't do it in a huge amount once. Do very many small amounts, and that will increase the contrast. So let me see if you can make out the difference here. So here it is with the HDRMT. Here is 1. This is very hard to see. 2. 3. Okay, yeah, hopefully you can see that. So here it is before. Here's one iteration of unsharp mask. Here's a second iteration of unsharp mask. You can see these features now are starting to show up much, much more. Here's the color adjustment. And now we're getting very close to what would be kind of the last step, which is to add in these stars. Let me see if I did anything else. I don't think I did. Let me just see if I did anything else. No, I think that's just changed the black point. One thing that I did do is I tried to bring in some more blue, but that was about it. So the last step I'd like to show you is actually bringing in the stars. Let me just show you here. I brought in a little more blue, but this was the final result that I ended up with for my starless version of this image. And now the last thing to do is to just bring in the stars. So let me just very quickly show you that, because I want to explain one idea behind the stars. I made the RGB image from those RGB images. So I made a final RGB image here. And then I used PCC, and there was nothing special about it, photometric color calibration to do its job. And then we get this result right here. So this image is still in its linear form. And what I needed to do, of course, is I need to get just the stars. And there's a trick for getting the stars from an image like this. The first thing, though, that you need to do is decide what level you want the stars to be when you grab them. Because what you need to do to get the stars is create a starless version of this image. And then you can grab those stars in a method that I'll show. But you might not want the stars to be overly bright. So you might want the stars to look dim. So let me see if I can show you this. Process, yes, screen stretch. Thank you. This is the version of the image that I stretched it as. So I chose to stretch the image with just showing the stars. I mean, you can actually see the nebula in here, but this is almost like a star reduction. So I don't have this, I didn't leave the image stretched. Let me just go back here. I didn't leave the image stretched in this form here. These stars are really, really big and kind of bloated, right? So it's almost like I'm doing a star reduction. if I choose to stretch the image permanently in this form, sorry, I went too far, in this form, which is right here. So then what you do is you create a starless version of this image. And again, that takes a lot of time. So I have that thing right here, I think. Open it. Yep, here it is. Let me press this so it's not like that. Good, here it is. So here we have the stars. Here's the starless image. Now I'm going to do a big stretch on them just so you can see the nebulosity, but just remember the stars are only being actually grabbed at that lower level. So here we have the stars on the left and we have the starless version here on the right. And to grab the stars, these two are, this comes from this image. All you do is you do what's called an unscreening. And I'm going to show that to you in Pixel Math, and I'll actually show you how it works. So I'm going to get out Pixel Math here. So how it works is the following. We're going to do this. We're going to do this. And you basically divide one image by the other. That's the whole trick. But you can't do it in normal brightness space. You need to do this in the inverted brightness space. So let me just show you that. I'm going to invert these images like this. And then you just divide one image by the other. That is the trick. The way that people are generally grabbing the stars from a starless image is that they subtract, right? They have the stars plus the nebula, they subtract the nebula, they end up with the stars. But that actually changes the colors of the stars, depending upon if the region where the stars are is bright or dark. And then you get this weird difference in brightness because of the background level and things. So this method that I'm showing, dividing one image by the other, is a way that actually has a floor value. You're going to see why in a moment. So let me just go ahead and do the original, which is, I have it here as image 68, because I don't have a good name. So it is image 68 divided by starless. This, let's create a new image. Sure, it's color. So here it is. This image has just the stars. So it's not a subtraction, it's actually a division. And the reason that it works is because when you have this image here, this starless image here, wherever the nebula exists in this image, it also exists in the original image, right? I'm trying to show that. Here it is. So when you divide one image by the other, where they're both exactly the same, it just goes to 1. Two values divided by one another that are equal go to 1. The only place where they're not going to be 1s are where there are stars, because that's the difference between the two images. And so that's how you get this. And in between, you're going to get something that's for your, because I have the H thing here, but for the brightness values, you're going to get something for that's the L value here, something that's very nearly 1. And the final step is just to invert this image. And now what you have here are basically zeros. In between the stars, you have 0, which means that when we blend this in by using the screen blending mode, it won't have any effect. And all we're going to get are stars. So we're not going to use addition or subtraction. We unscreen the stars by this method, and then you screen them back in using the screen blending mode. So now I can finally go back to the first workspace. I have a starless image of the narrowband starless image, and I also have the unscreened stars hanging out up here. Here they are. And I did it in just the way that I just showed you. But I want to show you that if you use Star Exterminator, Russ's stuff, you'll find that you don't need to go through those steps I just showed. You just press the button here and it gives you this image. So it gives you the unscreened stars. But how I just demonstrated that division with the inverted thing and inverting, that's how it works, and that's why it works. So you take the unscreened stars here, and now we're going to put them into this image by using Pixel Math. Where is it? I don't know. It's probably in the other workspace. Let me get Pixel Math again. So the expression that I want, there is a cool operator so that you don't have to have all those, little inversion signs for, there's a formula for the screen blending mode, but you can use the cool convenience function here all I need to do is take the two images. So I have Rosette here, starless. That's this image right here. And then I have my unscreened stars, like that. And then I just tell it the operation that I want, which is the screen blending mode. And then I should be able to produce an image that's going to end up with stars in it. Now, I want to be a little careful here because I want to show you my end result. And so what I'm going to do is make a copy here, a clone, and I'm going to add the word clone because I don't want to mess up my own work. I get so confused if I do that. I just want to show you it should work. Does it? Or did I make it? It does. Look at that. So now what we have is an image with the original stars, and they look good against a dark background here, but they also look good in regions where, you know, there's nebulosity and all that kind of stuff, and they retain basically their colors. Now, there's some, you know, some people might argue that there is a slight difference in color that you can still get depending upon the, you know, where the overlap in that nebulosity is, but it looks pretty good to me. And this is kind of the same method that I've always been using, but now it's kind of formalized in the pixel math sense. So that's how you make this thing. So now I'm going to close this version here. And I think if I just go forward with my thing, I should be able to get to my final version of it, I hope. No, maybe I just actually left it in that form. Let me just make sure I don't have some final thing here. I can't remember if I put a final on here or not. No. But let me go ahead then and show you the final version that I have on the web, which is this here. So zoomed out, you can certainly see the colors, and I was trying to go after getting these structures within the nebula to show up better than they would have otherwise against the HA and the O3 for the S2. And in addition, those colors are different. This is a pink color compared to this more deeper red color on the outside. And so we have a different coloration depending upon the features that we wanted, because the color modifiers allowed me to do that within this region. Now, everywhere else, it's pretty much living as it was because there isn't as much overlap. The S2 out here and is really dominating a lot of this filamentary structure. One thing I did need to do is to protect two areas in this image. There was one area that was just super bright here and another area super bright there that I protected with a mask when I did the color adjustment that I showed, because the saturation just went absolutely crazy on those two regions. But other than that, I've shown you all of the steps that I did to create this image. You should, of course, look at Russ's version of this image, and you'll see how you can get very different choices. Now, Russ is, of course, brilliant, and his eye for doing this, especially in the color sense, is just superb. So the vibrant result that he gets, he has a magenta version of his, basically his S2 and his hydrogen alpha. And then in the center, his O3 is this super vibrant blue, little bit of green in there result with a lot of contrast for the dust lanes and so on. But what I would say is that the difference that my image has is that some of these structures on the inside here, you know, this is mostly, it's just magenta mostly. It's either magenta or this, I mean, it's a beautiful color, teal, where I was trying to differentiate in those colors by using the modifiers that I was getting in my final result here. So it's a different rendering of the data using this kind of different technique of color modifiers. That's what I wanted to show tonight. And I hope that some part of that you'll find useful in your processing of narrowband data. So with that, I'm going to pause a moment.
And we're reaching for our little mute buttons to get off the mute.
Okay, sure.
And Jeff just Jeff and I just had an exchange over in the comments. A couple of people were commenting that they like your some of your other programs that you do too. So anyway,
Okay.
are there any other questions out there, people in YouTube land? We got to get everything in there. If you've got any more questions. So Adam, that was as usual, wonderful. Even Jeff was able to follow it. He remarked, so something was going pretty good. And it is interesting how much detail you can get out of all that stuff.
Yeah. So
yeah,
one
go
of the things, this is the kind of stuff that I cover in my Horizons part of the instructional stuff that I do. And I just want to say that the reason is because I wouldn't put this in my more fundamentals area. I mean, it's just too many, one-off steps. It's more of the artistic stuff. A lot of people, and this I think applies to a lot of instructional videos in general, they want to see this stuff, but it really relies on a lot of other foundational knowledge, I would say, like the use of pixel math, or an understanding of taking multiple images and blending them together, all that kind of stuff. So I just want to say that that's for me why it lives in a different area on my website, but it's also why it's hard to show this kind of stuff in a YouTube video or whatever. It just takes some doing and that kind of foundation to be able to present it.
There was a question, I think, still hanging around. Who was it, Tarek? Asked if you were using Star Exterminator or StarNet 2, and I've lost it.
Well, what's interesting is that Russ has come up with, let me see if I just happen to have it here. Oh, that's hard. 1 second. It's not showing up here because I've messed around with too many images. I could probably find it quickly. 1 second. It's hard. Does anyone see recent? How do I do my recent things? Hold on. Where's recent images or whatever they are?
And it was Xanthus's question. Do you use StarNet or Star Exterminator?
Okay, so the answer is, I was going to show you an example, but at the moment I'm using Star Exterminator because Russ changed his algorithm, and he's improved it rather dramatically. So I was really happy, especially with how it handles images like this that have undersample data. That is particularly in a star-crowded field. That's really, really tough for any of these neural nets to kind of handle. And Russ has recently added some interesting training, apparently, to his results, and it looks really good to me. So the answer is, for this data, and so far going forward, I've been using Russ's stuff.
Okay. And I'm sure that next month or the month after that, something else new may come up.
Yeah,
so,
that's true.
And you will be one of the people who will be bringing it to us.
We will try. That's always a tough thing to do, but yeah, definitely try to do that.
There's a lot of people have made some comments about your show, and they really appreciate it. Next week, we've got Jacques coming in here, and he's going to be finishing his explanation of how to take his pictures to some pretty beginning pictures, how to plan an evening and things like that. Jacques is still here, so he's here. And we will see you all next week. Is there anything else? Okay, Terry, I think you're in charge tonight. You can take us out. Oh, if we got... You can find out his website and go visit it.
I just put up my website just because it's
okay.
The right thing to do.
Okay. Okay, go ahead, take us out, Terry.